Alright, so in this video I'm going to be covering kinetics, which is topic 8 of AS Chemistry, Unit 2. And this is a really simple topic. There's a few ideas you've got to get your head round, but it's not hard at all and it should be quite a quick video. So kinetics, what does it actually mean? Well, kinetic energy is like movement. So if you think of like kinetic learners or whatever, it's just movement. So it's basically how the particles move and how they can react. And what kinetics fundamentally comes down to is rates of reaction. Yeah, how fast reactions can occur. Now, a lot of this sort of idea comes from collision theory. Now, it is like a section within this topic, but there's not actually that much to learn about. It's like you can explain it in a paragraph. Collision theory is the idea that for two particles to react, they both have to have the correct energy or activation energy, and they both have to be in the correct orientation. Now, in a reaction, most of the reactants collide and they don't have successful collisions, so they may not be in the correct orientation, so one may be like swung round and hit another, and the other time that it won't happen is if they don't have the right energy. So one might have enough energy and the other one doesn't, so a reaction doesn't happen. But if these two things are satisfied, then a reaction can occur and then your compound is formed. So that's basically collision theory. Now, we have to look at the factors that affect the rate at which this can happen. So what we're effectively doing here is messing about with, we can't really do anything for the orientation, but we can increase the rate at which collisions happen, and we could lower the activation energy with a catalyst, and that would increase the number of particles with activation energy, so there'd be more successful collisions. And each time I say successful collisions, you just need to think a reaction occurring, because if you have a test tube reaction, there are thousands of collisions going on between the reactants, but most of them are not successful and do not create the product. So you may have seen this sort of graph before, which is called the Maxwell-Boltzmann distribution curve. I'm going to label the axis up. So on the x-axis is energy E, and on the y-axis it's the fraction of particles with energy E. You need to know how to label these axes up because it does get asked in questions like the one later. You also need to know what this curve means. Now, we have jumped forward a little bit, but if we just step back for a second, what actually affects the rates of reaction in a test tube? What can we do to it that would change how fast two things react together? So it's really simple. There's increase in temperature. We can increase the pressure if it's a gaseous reaction. We could increase the concentration of solutions if it's a solution reaction. And we could use a catalyst, and we could also increase the surface area of the solid. Surface area of solid, and that's simply done by powdering it or breaking it up. These are the things that affect the rates of reaction. Why do they affect the rate of reaction? Well, this graph can effectively help explain that. And this isn't actually the complete graph, because there are a few points you need to know before we investigate what happens when you start changing stuff with it. So this will be the activation energy here. So that's written as E and then little a. And then over here we have the most probable energy. So that's MP, which is right at the top of the peak. And then just off to the right of the peak we have the average energy. So that's average energy. My handwriting's abysmal, I apologise. Yeah, so this always happens, and you may be like, why is the most probable there and the average there? Think of how averages work. You've got some values up at the top end, some values at the bottom, so when you average them out, you'll get something roughly in the middle. But the most probable is where most statistically likely a particle is to be there, which is obviously right when it goes with the curve. You don't really need to understand like why it's like that, I guess, but you can get away with just knowing that it's like that. So this is what you need to remember: the y-axis, the x-axis, and these 3 points along the curve. That's vitally important. You need to get that in your head before you start messing about with the graph. But let's start messing about with the graph anyway. To start with, we need to understand that the area under the curve is the amount of particles. So if you found the area within this curve here, right, that's the number of particles you have within whatever you're doing. Like if it's in a test tube, within the test tube, right? So the activation energy point here, if you found the area of this bit beyond it, this bit I'm just shading in now, then that would be the number of particles that can successfully react together and form a product of the reaction. So if we added a catalyst to this, what would that do? So you should all know the definition for a catalyst, which is it provides an alternative reaction pathway without getting directly involved in the reaction, reducing the activation energy. So on this curve, what it would look like is if we added a catalyst to this reaction, there would be a new point. We'll call it E and then cat. So imagine that's the activation energy with a catalyst. What's that done? Well, that's effectively introduced this new area here, which I can also shade in. Now that area, and that obviously there's a larger area there now, so that means there's more particles with activation energy, and therefore more successful collisions can occur because there are more particles that can react together. So that's how a catalyst would increase the speed of a reaction, because there are more particles, so it's more likely they're going to bump into each other and collide, and successful collision or reaction occur. So that's how catalysts work. Now we need to look at how, I think the next way to go from here is pressure. So what does pressure do? Pressure increases the rate of reaction because when a gas is compressed, the particles occupy a smaller volume. That means they've basically inherently got a little bit more kinetic energy to move about with, and collisions are more likely to occur. Think about it, if you got into an elevator with 6 people, you're more likely to bump into each other than if you went into a field with 6 people. It makes sense. So it has no effect on the graph then. So if you were asked a question about what would happen to like the activation energy or some like average energy or whatever, then you know that it would stay the same, because although they are more compressed and they're more likely to bump into each other, the graph still has the same shape. It doesn't alter the graph at all. This is the same for increasing the concentration of a solution, because although you've increased concentration and there is a larger area below the graph, the shape is exactly the same. Over time, however, both pressure and solution concentration, the rate would then fall because obviously the concentration or the pressure would decrease as products are formed by the reactants. So over time, it's sort of like the reaction would plateau off at the end, which is a bit of a weird concept, but if you can get these ideas nailed in your head, then that's good. So if you increase the concentration of a solution or increase the pressure, the graph remains the same shape. There may be a larger area below the graph as there's more particles for an increased solution concentration. What does make the graph change shape, however, is an increase in temperature. Okay, so I've redrawn the standard graph like this, and we have our activation energy on it. So what does an increase in temperature do? Well, if we increase the temperature, I'm going to show it with a different pen, the graph does change shape, as you might expect, because, I'll just draw it on now, I'm going to go through that, never mind. What you've actually done is given the particles more kinetic energy and energy in general. So therefore, the most probable energy, which is there, I'm going to use this pen, let's write MP, has moved as the peak, and this is vitally important that you remember this, when you increase the temperature, the graph shifts to the right and lowers. And as you'll notice, the particles with activation energy, as that still remains the same, has increased as there is a larger area below the curve, so therefore more particles with activation energy. So it only crosses the graph once. It doesn't go as low down as the standard graph in terms of the downward peak where the activation energy is. What happens when you decrease the temperature? And effectively it's the exact opposite. The graph shifts to the left and gets taller than the standard graph. So I'm going to draw it on with a blue pen, if I can find it. There we go. We go up and we go much lower. The most probable energy has decreased, as would the average energy do. I've just wrote the most probable one on because it's easy to see with the peaks, and it's become much taller and shallow at this end. Notice that whichever graph you get asked to draw, it will only ever cross the standard graph once. It never crosses twice, and that's a marking point on most exams. And then that's the same for like everything. And the other thing is, the activation energy for a decrease in temperature has, like, the graph has to be lower than the other one, obviously, as there are less particles there, so as there's less successful collisions because they don't have as much kinetic energy. You can have a look at the how science work questions. I think I'm not really ever going to cover the how science work stuff in these videos because I'm more just doing the sort of the actual topics, but that is how you do kinetics. That's the whole unit, like, pretty much done. Now, I was going to get like a little question thing, but I did have an exam paper floating about somewhere. Here we go. So this is the June 2014, so this is last year's test for me now. That's on there, and I think here it is. It's question 2. I already filled it out because I took one go doing this video and then messed up a little bit, so I'm going to do it again. So the first question, we'll read it from the top. Figure 2 shows the Maxwell-Boltzmann distribution of molecular energies in a sample of gas at temperature T. So this would be the standard curve, the one that's not all messed up and that I've written on. That's the standard curve. One of the axes is label the other axis. So this is labelled energy. So the y-axis is fraction of particles with energy E. As I said before, you need to know the axes. You do get asked to do this quite a lot. Like, they may miss the bottom one off, they may say put the most probable energy on, put the average energy on, put the activation energy on, whatever you need to do. State why the curve starts at the origin. These curves, maybe I forgot to mention this, always start at the origin no matter what you do to them, if you increase or decrease the temperature. The reason for this is there are no molecules with no energy. There's just no molecules. And that's all you need to write for the mark. There are no molecules. 2C. Let's move this up a little bit. With the following, which of the following A, B or C describes the value of Y represents in figure 2? So we can see Y is here. We can get a ruler. Most of the time it just helps to use a ruler. And we see that it is the peak, so that would be the activation energy. And activation energy, what am I on about? Most probable energy, because the activation energy will be down here, and the average energy would be about there on the standard graph. Just ignore the one I've drawn on for now. So our choices are energy needed for a successful collision, the minimum energy needed for a reaction to occur, that would be the activation energy, that would be, A would be just the area above the activation energy. Sorry about that, that's my phone. And C is the most probable energy, so it's definitely C. Next page. On figure 2, draw a distribution of molecular energies in the sample of gas at a high temperature. So this explains what I've drawn. I've drawn the graph lower, and it only crosses once, which is a marking point. The first marking point is for drawing it lower and shifted to the right. So the most probable peak needs to be further to the right. And lower down, that's mark 1. Mark 2 is a combination of things. It's like roughly the same area, which is bollocks, to be quite frank, because you can't really, it's hard to judge, but as long as you draw it sensibly, you should be okay with that. I think you get let off. You need to only cross over once, and I think the third mark's something stupid, like don't do something, like don't draw it wrong, but it's like you won't get the first mark if you drew it wrong, so it makes no sense. Anyway, that's that. The last question, the pressure of the original sample of gas is doubled at the same temperature. So that's at the constant temperature. State the effect, if any, on the change of value of Y. So we know that the particles are closer together and there's in a smaller volume, so more likely to react, but there is still the same number of particles. They all basically, they're closer, but it will not affect the shape of the graph. So on the change in value of Y, that's the most probable energy. There's no effect on the graphs, therefore there would be no effect in the most probable energy. And that is that. So that is kinetics done. Now if you've got any questions, just ask. If you want us to do a how science worksy thing, I might do, but I don't really like doing them because it's just a bit, I think you just need to like read through it and then you get the how sciencey worksy stuff. But yeah, I think it's all on page 140 of that textbook, which I always have, which I'll just show you. This textbook on 140 is when I think it starts going into catalysts and stuff. Yeah, there we go.